We're trying to flip this ball, but this one is land straight. Even though it looks pretty simple, there's a lot of factors that go into the bottle flipping. So all you have to do is just hold up. Let's explore the factors and the physics behind the bottle flip.
When we flip a bottle, many aspects can be considered for the whole momentum. Commonly, the air resistance, throwing velocity, and acceleration through gravity. However, Newton's three laws and even more complex concepts such as angular momentum and fluid dynamics are also considered. Let's walk through them. But first, let's consider how a bottle flip works. When the bottle is flipped, we have to first analyze the substance in the bottle. If we observe the water in the bottle as it flips, we can see that the water does not reach the top of the bottle. But many other factors such as speed, mass, and the center of gravity must be taken into consideration. Shifted along the side when rotating, there is a change in the center of gravity, thus leading to change in water distribution as the center of gravity is moving with the mass of water. However, during the rotation, the water splashes up and down, never quite making it up and around in a full rotation. This is caused by a phenomenon called angular momentum, which applies to any object moving around a point, such as our Earth orbiting the Sun. A rotating object's inertia will be affected due to these factors. This is why the ideal bottle flip volume is 1/3 of the container in what we're trying to flip. This is because the weight of the water is more than of the bottle, which means the water can overcome the angular momentum and resist being pulled into the bottle's overhead spin. Thus, consider 1/3 of the bottle as a sweet spot for the balance between the bottle, and that will ensure a successful bottle flip.
Let's test it out. Liquids are unlike any other solids in that their molecules are able to move freely and independently from one another. That characteristic leads to another important concept, fluid dynamics, how the water moves inside the bottle. We'll look at 3 different bottles, each bottle varying in mass or amount of liquid present in it. One has a full quantity, the other has very little quantity, and finally one with 1/3 quantity. Before we start, let's consider how Newton's laws play a role in ball flipping.
Newton's first law states an object at rest will remain at rest unless acted on by an unbalanced force. This is also known as inertia. This is implied to a bottle simply because the bottle is at rest. However, when the bottle is flipped, the bottle wants to stay in motion unless acted on by an unbalanced force, in this case the ground. This is Newton's second law. Lastly, as the bottle hits the ground, there is a reaction force from the ground upwards on the bottle, which is the reason why the water accelerates upwards when it comes to contact with the ground. This is Newton's third law of that every action force there is a reaction force.
Welcome to the laboratory, ladies and gentlemen. Now we're going to pay our boy, Sir Isaac Newton, some tribute by now performing the experiments. As you know so far, we're going to start off with the full physics juice. Now, as I drop this, you can see that it's very unstable. This is partially due to the fact that it has a very high center of gravity. If you drop the less physics juice down, you can see that it's also very unstable. This is due because of the very low center of gravity that it has. But if you do the 1/3 bottle, you can see that it stays upright. This is due to the fact that its center of gravity is just balanced enough that its mass of water and its mass of the bottle stays balanced, so it will always round up around.
Now, let's look at the full rotations. As you can see, too much water means that the bottle will be spinning like any other solid object. And since there's no room for water to splash around, it is evenly distributed. So it will not likely to land upright as the weight is all the same. Thus, will exert a large amount of force downwards on the ground, and the ground will exert a force upwards on the bottle, causing it to jump and fall. Too little water means that there will not be enough mass to slow down the angular momentum, and the bottom will be flimsy. With 1/3 of the bottle, it spins at just the right volume, which allows the water and object to spin easier with respect to the angular momentum, because the water will easily move around and the center of the gravity will be more apparent. Angular momentum, angular momentum. What are these guys talking about? This might be the question you guys are asking right now. Well, angular momentum is the quantity of a rotation of a body, which is a product of its moment of inertia and its angular velocity. Also represented by the equation shown, where L represents angular momentum, I represents moment of inertia, and W represents angular velocity. The moment of inertia is a measure of an object's resistance to change in the rotation direction. Moment of inertia has the same relationship to angular acceleration as mass to linear acceleration. The flip of the bottle is dependent on the mass of the object, the speed of the rotation, and the distance from its center of gravity. As the bottle is flipped, there is a change in the center of gravity, which leads in a change of distribution of water. This is what affects the rotation of the bottle. This rotational change is the moment of inertia for the water bottle and its liquid. This rotational inertia works off the axis of rotation, and mathematically, the mass times the square of the perpendicular distance to the rotation of the axis. The water rotating in the bottle is affected by the torque and angular acceleration to stick the landing. The angular momentum is similar to the classical sense of momentum, where an object moving will not change its motion unless acted upon by another force. This angular momentum, the same concept is applied to rotation.
So basically, as centrifugal force keeps the water at the bottom of the bottle during its spin, that also dictates where the plastic container's center of gravity is. The heaviest part of the bottle is pulled towards the ground. This pull is because of the centripetal force. This concept is similar to spinning a bucket in a vertical circle. As the gravity will pull the water inside the bucket towards the earth, but will also pull the bucket towards the earth. So they're moving together. Above your head, the bucket and water are moving forward, and they like to keep going that way, but the string you are using to swing the bucket yanks the water and the bucket back into the circular path, exerting what we call a centripetal force. The water and the bucket are both being pulled by the force of gravity to move downwards, but are redirected into a circular path by the centripetal force of the rope. Because of this, the water stays neatly in the bucket, just like passengers stay in their seats on the roller coaster. So in summary, to have a successful water bottle flip, the bottle must be filled with 1/3 of water in whatever container it is in. The water and the center of gravity must rest in the base of the bottle. When the bottle is tossed, it rotates, but since the water is free to flow, the fluid does not all rotate with the bottle. Instead, it sloshes around. This is known as angular momentum. As a light bottle spins, the angular momentum is transferred to the heavier water. The bottle spin is slowed. The now nearly unspinning bottle falls with gravity and lands straight upright on the table.